So now we're recording. If anyone is unable to join us right now during this live session, they'll be able to go back into the web course after this meeting and watch this video. And so what I'm going to do first is share my screen with you so that we can go through, first off, these few PowerPoint slides. Okay. So on Tuesday, we talked about conducting a SWOT analysis, and we talked about identifying costs and actually conducting a break-even analysis, which I think are very useful tools, and they're things that I personally use all the time when faced with these types of questions or decisions. And I feel like you guys are really great and catching on really fast with this stuff. So I wanted to just give you a little bit more on this topic today that will give you another tool to use when your decision involves something more long-term. And so anytime you have to decide about whether to purchase a piece of capital equipment, for example, and capital assets are by definition those things that an organization owns that will be used to pursue the mission of the organization for a period that extends beyond 1 year. And so sometimes you've got major decisions and big ticket items that you need to think about and analyze in terms of whether it's a good idea to acquire them. And sometimes you may have programs, or you may be applying for a grant that spans more than 1 year. And so when this is the case, it's beneficial to consider the time value of money in your financial decision making. And so today, briefly in the first half of our session, I'm going to talk a little bit about what the time value of money is. I'm going to introduce the concepts of compounding and discounting. We're going to talk a little bit about present value and future value. And then we're going to finish with putting it all sort of together to do a net present value type of analysis. So the time value of money is a very important concept for projects that involve both costs and benefits, or maybe cash outflows and cash inflows that extend over a long period of time, or at least extend beyond the current year. And so in making these types of financial decisions, it's very necessary to estimate the costs and the benefits of these projects with the factor of time included. And so the time value of money is the notion that a dollar today is not worth the same amount as it is in the future. Because if we have money today, then we could invest that money and earn a positive return during that time period when we would otherwise be waiting to receive the money. And so the idea here is that there's actually a cost of capital opportunity cost whenever you have capital assets purchased, or you have these situations where you're making decisions about things that extend over multiple years. And so generally, if you have a capital asset that you're trying to consider whether you should acquire, or you have these long-term programs, you need to recognize that oftentimes the way in which you can acquire these assets and pay for them is by borrowing money, taking out a loan, or entering into a lease, and therefore you'll be paying interest in addition to repaying the principal amount that you borrow. Or you can think about it as, if you use the cash that you have on hand, then you've decided to not invest that money elsewhere, and therefore you fail to earn a return on that investment. And so time value of money calculations really are rooted in this assumption that either we have to borrow money to invest in a capital asset and therefore we have to pay interest, or we'll use resources that are currently owned by the organization, in which case we will forego the return that we could have earned from the best alternative use of the resources. And so the computations or the calculations that I'm going to go through with you actually help to compare investments to a specific expected desired cost of capital, which oftentimes is just quite simply the interest rate that you otherwise could earn on an investment. And so the important thing to keep in mind here is that when we're doing time value of money calculations, we're really thinking about the costs and the benefits, or the inflows and the outflows on a cash basis. We're not thinking about this on an accrual basis, which is what you're more likely to use for budgeting and for your journal transactions, for your financial reporting and recording financial events. So here we're talking specifically about cash flows, the flow of actual cash. So the basis here of the time value of money is simply compound interest. So compound interest is the idea that when money is invested going forward in time, at some point, the money you invest actually starts to earn interest on itself. And so compound interest is essentially what we use to determine how much of a certain amount of money that's received today is likely to be worth in the future, assuming, of course, that we can earn some rate of return on this investment. And we can do these calculations to find these amounts out through the processes of compounding and discounting. So discounting, well, compounding, as I just mentioned, is the process of finding the value of some point in the future of a dollar that we've invested today at some specified interest rate. Discounting, on the other hand, is the exact opposite. It is the reverse of compounding. So discounting is when we're coming backwards in time, but it's useful because it helps us to determine how much of an amount of money that we might receive in the future is going to be worth today. So discounting is essentially the process of reversing all of the compound interest that would occur between now and in the future. So you can see here, this is showing you, oops, sorry about that. This is showing you on this graph that if you have your starting principal, let's say in year one, we decide to invest $100 in the bank. And according to this, we are going to see 12% interest, which I realize seems very high if we're thinking about this in terms of like a savings account or something like that. We're talking about investments that are going to earn a higher return than just a bank account. So we can start off here with a $100 principal invested to start. And if we were to apply 12% interest rate to that investment, we can see that $100 times 1.12, which is the same as multiplying $100 times 12%, gives us $12. And so at the end of the first year, with a simple interest calculation, we would earn $12 each year, and only $12 each year. So we can see that our original $100 here is only getting $12 added to it each year. The difference with compounding is once we have our initial starting principal, and we multiply that by 12%, and we get our ending value of $112. Now, the difference between simple interest and compound interest is that we use the $112 to calculate our year 2 interest. And so we can see here that just because the $12 that we earned in the first year of our investment also earned interest in the second year of our investment, we end up with $125.44 instead of $124. So we earn an additional $1.44 simply because our principal, once it starts to earn interest, then also begins to earn interest upon itself. So of course you always want, if it's an investment, you always want your interest compounded. And it's also helpful to have that interest compounded more frequently, because the more frequently you add interest onto your amount that you've invested, that interest begins earning interest sooner, and you can see how the snowball kind of helps grow your money in that regard. So as I mentioned, the processes of compounding and discounting are very important for determining present and future value. Present value is simply the discounted value of an investment at its beginning point or any point beyond the end of the investment. So present value is always today. It's always going to be time period 0 because it's happening right now today. So the present value will always represent today's value of a future investment. The future value, again, it's just the opposite. So the future value is going to represent that compounded value of an investment at any point after its original starting point or any point after the beginning of the investment. And so the future value represents the value of a current investment at the point in the future when it will be paid or received by the investor. Okay, we're going to do a little bit of math here, but I promise it won't be too scary. These are really very straightforward equations to use once you get the hang of them. There's only a few pieces of information that you need to be able to identify here. But what we have here is an example that uses annual compounding. So the interest will only be compounded one time per year. I'm using annual compounding for this example right now because it keeps the calculations a little bit simpler. But in reality, of course, most compounding is going to be done more frequently than annually. And as I said earlier, the more frequently that the interest compounds, the better off you are as an investor. And so we can see here that there are two fairly simple equations. The table on the top is quite simply just reiterating the table that I had on this slide. So you can see from this slide, all I've really done here is copy the same information roughly from the previous slide. And then at the bottom here, I have the actual formulas for future value and for present value. So for any type of mathematical formula, and these in particular, you can see that there's 1, 2, 3, 4 pieces of information, which means that go into the calculation, which means that we need to know 3 of the 4 pieces of information, and then we can solve for the 4th piece that we don't know. And so here, if we want to calculate the future value, that's going to be done by taking just the number 1 and adding it to the interest rate, Now, it's important to keep in mind here that this I that's representing the interest rate here is actually going to be inputted into this formula in decimal form. So instead of 12 or 12%, you want to incorporate it as 0.12 in decimal form, okay? Now, N here is going to be the number of compounding periods. And then to finish the calculation, this is a multiplication sign. You're going to take this part of the equation and multiply by the present value. So we know from this table up here that our present value is the initial $100 that we invested. We know that we receive 12% interest rate per year because it's compounded annually. And we know that we want to invest our money for 4 years because that's what we've decided, and that's the amount of time that we have. And so this equation becomes 1.12 to the 4th power times $100, which equals this value that you can see here, having done all these calculations by hand, adding 12%, each of the 4 years, we end up with 157.35, which is, of course, the amount that we have down here in terms of the future value. In terms of our present value calculation, that is going to be equal, present value is going to be equal to the future value, but now divided by 1 plus I to the n. So we're going to take the future value that's in our table, right, or that we know, and we're going to put that into the numerator of our formula here. And then we're going to divide by 1 plus 0.12 to the 4th power. And that simple calculation gets us back to our $100 present value. Now, here's one little trick with these calculations that you just have to keep in mind. And we will go through a couple more examples before I'm finished. But here, you have to remember that the I reflecting the interest rate and the N reflecting the compounding periods, they must be adjusted for the number of compounding periods per year. And so what I mean by that is the annual interest rate, or the I in this formula, absolutely must be divided by the number of compounding periods per year, so that what you're really putting into the equation is the interest rate per compounding period. So for example, here we're using a 12% interest rate compounded annually, but I said it's quite common for interest to be compounded more frequently. And so if we were alternatively to say this interest rate was going to be compounded on a quarterly basis instead of an annual basis, we would quite simply take the 12% interest rate, or the 0.12, and divide by 4, because there would be 4 compounding periods per year. Along with that, we also would adjust the N here by multiplying the number of years by the number of compounding periods per year, so that in the formula here, we're actually using the total number of compounding periods for the entire investment. So again, I needs to be divided by the number of compounding periods per year, so that the I that we're using in the formula reflects the interest rate per compounding period. And then the N in the formula needs to be adjusted by taking the number of years of the investment and multiplying it by the number of compounding periods per year, Again, so that the N in the formula is actually reflecting the total number of compounding periods for the entire investment. Okay, so here is a really, really great practice problem. Unfortunately, this has yet to happen in my life, but perhaps someone has offered to pay you $500,000 in 40 years. I'm still waiting myself. And so let's say that you could invest your money at 4% interest rate with quarterly compounding. And so we want to know how much that future payment would be in terms of today's dollar. Again, remember, we're thinking about this in terms of the opportunity cost of capital, right? So if we have to wait to receive this money, we have to wait 40 years to receive this $500,000. Because we don't have it in our pockets now or our bank accounts now, we can't actually earn that 4% that we could if we had the money now and chose to invest it for 40 years. So it's going to be worth less to us in today's dollar terms. So in this problem, we're asking what the present value is, okay? So $500,000 40 years from now sounds like an amazing deal. But what does that mean for me today financially? What is that equivalency? So we know that the future value in this example is $500,000. We know the interest rate is 4% per year, but in this example, we're compounding that interest on a quarterly basis. And so we need to divide the 4% annual interest rate by the 4 quarters in the year so that we're actually inputting into the formula 1% interest per compounding period. Similarly, we need to adjust the N here because we've got 40 years that we need to wait for this, this nice payoff. However, we know that the interest will be compounded 4 times per year, so we multiply the 40 times the 4. So our present value formula, similar to the previous slide, is 1 over 1 plus I to the n times future value. So 1 over 1 plus, this is the 1% that we calculated by dividing the 4% annual rate by the 4 quarters per year. And then this is our n, multiplying the 40 years times 4 compounding periods per year times our future value here, which we know is $500,000. And I don't. So I will tell you the answer. I apologize, I don't have it written on the slide here, but the answer is actually in the notes portion of the PowerPoint slides that we put into the web course today. So you do have the numerical answers, so you can go back and redo the calculations yourselves and make sure that you're coming up with the right answer. So this present value ends up being $101,753.70, which is quite a discount, right? I mean, gosh, $500,000 in 40 years is only a little over $100,000 in today's terms. So one more quick practice problem. This is a topic that I teach very regularly for students in master's degree program in public administration and nonprofit management. And because I'm also a little sadistic, one of my favorite things to do is to show my students how much they're actually going to be repaying in student loans when they finish their degree programs. And they never like the answer to this. So I didn't quite make this practice problem quite so disappointing, because it's hard times and we want to at least keep things very upbeat and happy right now. So this is just a more generic, suppose that you took a loan out for a piece of equipment or a vehicle or whatever the case may be. And so you took a loan out for $20,000 from your bank, and they're going to require you to pay 6.25% interest, which will be compounded quarterly. And so if you take 15 years to repay this loan, how much in both principal and interest will you actually be paying back to the bank? That's the question of the day, of course. So we know that the present value here is $20,000 because that's the amount you're borrowing. We know our interest rate is going to be 6.25%, but we're going to divide by 4, again, because it's compounded quarterly. N is going to be 60 because we've got 15 years times the 4 quarters per year, which is a value of 60. And so when we do these calculations, we end up with a future value of $50,702.92. So more than double, about 2.5 times what you actually borrowed, you end up repaying. And so that ends up being a little bit shocking for people when they see this for the first time. So here's a little bit of a tip. If you have debt or you have any sort of borrowing or loan or credit card or whatever the case may be, early on when you start to repay that loan or you start to pay that debt, most of your payment is going toward the interest and not actually reducing the principal in any meaningful way. And so if you can pay a little bit extra, and the rule of thumb that tends to be really helpful is if you can split one entire extra payment a year into 12 monthly payments, then that extra payment a year doesn't hurt the pocketbook too much, right? It's not quite as painful, but that extra payment goes entirely to paying off your principal. And that makes your principal go down faster, which then makes the repayment apply toward the principal faster, and you pay your loan off much, much quicker. You heard it here first. Okay, and then the last thing that I wanted to just mention as a really, really great analytical tool is to kind of put both of these pieces together in a net present value type of analysis. And so net present value is quite simply the present value of the inflows. Remember, again, we're talking about cash inflows and outflows in this conversation. So the net present value is the present value of the inflows minus the present value of the outflows. And this is a very common approach that's used to evaluate capital investment alternatives, again, that generate both cash inflows or revenues and cash outflows or costs. And so essentially what you want to do here, and again, also this is over a period of time that's greater than 1 year. And so what you want to do here for this method and this approach is to find the net cash flow in each year of the investment for each alternative and subtract the cash outflows from the cash inflows, so that each year of the investment or the project, you are calculating the net cash flow. And then you'll find the present value of each of those cash flows individually if they occur over different periods of time. And then the rule of thumb here, and I have an example on the next slide, the rule of thumb here is if the net present value is greater than 0, then make the investment, at least in terms of the financial decision. There could be other reasons to not make the investment or engage and implement the program, but from a purely financial standpoint, if the net present value is greater than 0, make the investment. And if you have to choose among multiple alternatives, it's usually advisable to rank the alternatives sort of in order of their net present values so that you can make the decision that has the greatest ratio of net present values among all of your choices. So here is a table that sort of gives you an example of this process. So we can see here we've got 4 years, and this is a surgery department for a hospital in this example. And so we've got cash flows happening each year, cash inflows happening each year. We've also got an initial startup cost of 5 million or 5,000. I think these might be in thousands, but oh, maybe not. Of $5,000. And then we've got probably like some maintenance costs as other cash outflows over the next few years. And so we're going to subtract the outflows from the inflows, which means right now in the present value, right now in time period 0 today, we have a negative 5,000 net cash flow. And then for years 1, 2, 3, and 4, we have positive net cash flows. So what we would do is this number is already in present value. Remember I said that today at time period 0, we're already at the present value. So you don't need to do a calculation for this initial $5,000. But what you will need to do is use the formulas on the previous slides, the present value formula in particular, and calculate each of these individually. And the reason you need to do that is because these all occur in different periods of time. So we've got a 10% discount rate that is being compounded annually, but for this 1,700, you only discount one time period to get back to the future value. This 1,500, you discount back 2 time periods. So each N in and the future value in the calculations are going to be a little bit different. And then in this problem, we can see that once we add all of these up together, we've got the negative 5,000, and then we've got the positive cash flows. But we can see here that the net present value is in fact negative, which makes this a bad investment. And so if I were your financial advisor, I would advise you against this investment unless some other things perhaps are able to be changed, like you can raise the price to bring in a little bit more income, or maybe that initial investment can come down in cost, or maybe just the maintenance costs over time can be reduced. There's a lot of managerial type decisions that would go along with the outcome from this type of analysis, and so that absolutely needs to be done internally within the organization, and other things maybe taken into consideration than just the financial aspect of it.